I'm going to discuss the CFT of just a single free scalar, and the basic question I want to ask is, what is the spectrum of primaries? And what I would like to do, if possible, is get to the point where we can also construct these primaries. So
this is a new topic now, right?
this is a new topic, right? So we'll still use symmetric group, but yes, it's a new problem.
So the previous topic,
Yes.
Can I ask?
Yes,
There are
absolutely.
signs of integrability anywhere?
So essentially, for these operators labeled by a graph, you are left with a sum of harmonic oscillators, which you can decouple and then solve exactly. When you start to look at something like LLM backgrounds, where you start to just excite one corner of the Young diagram, then it does indeed look like there's integrability. In that case, you can use the SU22 symmetry of the theory to fix the S matrix, and you can calculate the phase of the S matrix at strong coupling. And so I would say that we have some evidence that there's integrability coming out in those limits.
Also, the way you got the answer, it was already diagonalized. So you just had a harmonic oscillator.
Yep.
Usually finding the spectrum of multibody excitations would be in general difficult, right?
Yes.
So is it somehow better? How is it that you're ready? You already get many equations.
Okay.
Solutions to the beta ansatz equations.
So we didn't write a beta ansatz at all.
You did, but you got
yeah.
finally
We get some spectrum, exactly.
Yeah.
You
On a
know.
long spin chain, the way I would obtain the XY model was to write down the beta equations and so on.
Sure.
Which automatically happened somehow and
right.
got the answers.
Yep. So I don't think that, we didn't sit down and find a method to engineer the solution. So we solved it numerically. We thought we knew what was going on. Then we made a guess for what the answer was. We plugged it in and it worked. And if you ask me now, why did that guess work, or can you mimic this in other setups, I think the honest answer is no.
In the spin chain, the thing that's non-trivial is that the energy of two excitations is not the sum of energy of each excitation. The S matrix adds the phase that changes the quantization conditions. That's the way the equation.
Yeah.
He had nothing analogous.
Exactly.
It was just a sum of excitations.
Yep.
Because it was a long operator on which.
Well, even for a long operator, there's some quantization condition change. He's not seeing the analog of that, maybe because his length is 8.
Yeah.
So I think that the part that you're after is not there.
Exactly. Yep. Yep.
If the x's were order 1, the number of x's were order 1, then you would get the analog of the Bethe spectrum.
Exactly. Then in fact you'd be back in the spin chain land. Yep. Yeah.
Okay. But sorry. So
yeah.
just pushing along this line.
Yep.
If you have some order 1 number of x's and just 2 y's.
Yep.
Right. So when you think the spectrum can be obtained exactly?
No, I doubt it. I think in that case, probably the best language is to go back to traces and the spin chain. I don't think that this language would give any advantage. In fact, I think it would be a downgrade. Yeah.
But spin chain addresses not just the BPS spectrum, is that right? Or am I wrong about?
No,
everything. Yeah.
So the operators that you were considering are all BPS, right?
No. So what happens is if you draw the graph, so those graphs that you drew, you could have some edges that would move from the node and back to the same node. Those would be BPS. But as soon as you look at graphs where you let the edges move between the nodes, those are non-BPS.
Oh, I see. So you're saying that the open string executions on giant gravitons, those are. I see. So there's a tower of non-BPS executions of open strings.
Of these giants. Yeah. So if you have a single row, then it's completely BPS. And there you can actually match it to the spectrum that was obtained by, I guess it was Das, Matur-Yavitsky. And there it's all BPS from the Born-Felt action.
Yeah.
Their paper indicated what
long BPS excitations were, but they restricted themselves to
BPS, yeah. Okay, so what is the spectrum of primaries? So what are we doing? We have, let me just remind you, phi of naught is the primary, and what we would like to do is, we would like...
Not one matrix, just really.
No, just really one field for now, yep. So phi of naught would be the primary. This has got delta is equal to 1. I have to label it by 2 spins. Let's call it a left and a right spin. In this case, these would both be naught. Descendants in this multiplet would be symmetric traceless combinations of derivatives acting on the field. So this would be something with a dimension k plus 1. And the spin for this would be, what is it? K over 2, K over 2. And we also need to take into account the null state condition. So this guy saturates the unitarity bound, so you get a null state, and that is just the equation of motion. Some level 2 descendant is null.
So you're in 4 dimensions?
In 4 dimensions, yes.
And you're using SU2 times SU2.
Exactly, exactly. So what do we want to do now?
Be done even when there's no null state.
Yes, when there, absolutely it can be done when there's no null state, yes. Now, you mean when there's interactions?
Yeah, just a mean field theory with some different dimensions.
Okay, so we are busy looking at Wilson-Fisher right now. So it looks promising, but we're not finished. Yeah. So everything that I say will be for free field theories. Yeah. Okay. Now, so what do we want to do? Well, to get the full spectrum of primaries, you'd want to take products of the phis. And what would that be? Well, if I say that this is representation V, I would want, what I could do is calculate the character for the symmetric product of n copies of phi. And this would be the complete set of states sitting inside that space. And then what I would want to do is, I'd like to decompose this into some sum over delta, j left, j right. There'll be some integer, j left, j right, and some character, delta, j left, j right. So that's what I'd like to do. And the question that I'm asking is, what are these integers sitting over here? How can we get our hands on them? And then the next question I'd like to ask is, once we've counted them, once we know what these integers are, does that suggest a way of constructing these primaries in general? So that's the collection of ideas. So what do we need first? First thing that we need to do is to extract chi. And this is a very standard formula for that. So I'm just going to quote it. 1 over the determinant. Okay, so first of all, I could take the character of any element of the group. I'm going to look at the character of M, which is S to the dilatation operator, X to the J3 left, Y to the J3 right, and this is an element of SO42. That's the character that I want to calculate. So now I'll calculate the determinant of 1 minus Tm, and I know what this will give me. This is just going to give me a sum from n is equal to 0 to infinity of t to the n symmetric product to the n of m. So those are the characters that I want to decompose. And what's nice about that formula is it is very easy to write down what the determinant is. So there's going to be a factor for every single one of the states that you can build here. So in particular, if I think first about dimensions, there's one collection of states at every dimension starting from naught going up to infinity. So I will have 1 over 1 minus t s to the q plus 1. And at dimension q plus 1, I have to run over all of the spins inside that multiplet. So we'll have
This is somehow you're somehow quoting the formula for most statistics, right?
exactly.
So if you did a path integral, you get the determinant, and that is the partition function. For
Precisely, exactly, yep. So A and B is equal to minus Q over 2 to Q over 2. This would be X to the A, Y to the B. So that's the thing that I'd like to calculate. And once I expand this out, I'm going to set this character equal to the sum and try to find the ends. So that's the problem. How do you find the ends? So let's start off and massage this a bit. So let's say chi sum n of v. And I'm going to write this now as a function of s, x, and y, because that's how I've parameterized m.
A, B, and Q run over the states of one file's derivatives.
Good. So A and B runs over the multiplet, this multiplet, and Q is running over all possible dimensions.
Right, and that whole combination runs
Yep.
over the full state content of the things you get by acting arbitrary numbers as derivatives on one file.
Precisely. Yep. Exactly.
The later partition function.
Exactly.
Sorry, your V is this. Your V is
So this is the representation built on this primary.
on this primary.
Yep. So it's got delta is equal to 1 at level after you've acted with k derivatives, delta is k plus 1. That's the spin that you've got. This is a symmetric traceless polynomial. Yeah.
Just the representation of phi.
Precisely. Exactly.
How about the null state you have imposed it?
Removed it.
Removed it. Yep.
All derivatives modulo equation.
Because
Where is that taken into account?
it's taken into account by saying that this representation is traceless. So that means there's a k over 2, k over 2. And so this runs only over the states inside that rep. So it's already gone. Yep. Okay. So what we would like to do is to write this guy as some sum over characters. Now, let me just remind you what is this character. So I'm now going to write down the formula for that character. It is going to be s to the delta chi j left of x chi j right of y. That's the quantum number of the primary. And then what we have is we have this denominator sitting here. Now, remember how you would build the state. You start with the primary, and then you'd act with all possible derivatives. If you think about the derivative p mu, this has got delta is equal to 1. That's why there's a single s sitting in front of each of these factors. And it's in the 1/2 representation. So here you've got x to the 1/2, y to the 1/2, x to the half, y to the minus 1/2, and so on. So these four factors here correspond to the four components of momentum. If you expand these four factors out, you will start to generate all of the descendants. The character is a trace. Each term in the sum of the character should correspond to one state that you're tracing over, and you can read the quantum numbers of that state off when you expand this out. So those guys over there are just for the descendants.
What
This
was
is
the null
right.
state?
Okay, good. So
Only at n equals 2, right? There are only null states at n equals 2.
there's only null states at n is equal. Okay, there's a null state at n is equal to 1.
Yes.
Then at n is equal to 2, there's null states. So you
Oh,
can
okay.
deal with that. But let's just, for us, we're just going to take n greater than 2.
How do I know that there is no?
So the null states come because you've saturated the unitarity bound. Yeah,
Yeah, you cannot solve saturated.
precisely.
It's because delta minus j keeps increasing every time
Yeah.
you find that.
Yeah. Okay, so I think we can all agree that there's no content in this factor sitting at the bottom here. This is just for producing the derivatives. So what I'm going to do is I'm going to multiply on both sides by exactly that denominator. So let's get rid of that from here. And 1 minus s square root xy, 1 minus s over the square root xy. And there's another 2 factors there. So I've just multiplied that out. Next thing I'd like to do, I want to simplify this even a little bit more. How can I do that? Well, let's think about this character. If I've got, I don't know, let's say I've got chi 2 of x. This would be x squared plus 1 over x plus 1 over x squared. Now what I'm going to do is, I'm going to multiply by x minus 1 over x. Sorry, I'm going to multiply by 1 minus 1 over x. So what you can see is the x squared into the 1 over x cancels with the 1 into the x. So almost everything cancels. You're left with an x squared minus 1 over x cubed. So if I decide to keep only the positive powers, so that little greater than sign will say keep positive powers, then I will just get x squared. So by multiplying both sides by 1 minus 1 over x, 1 minus 1 over y, expanding and keeping only positive powers, I can replace this by x to the jl and that by y to the jr. Okay? So let me then write down the formula that I really want. So I want this. Let me just remove that. I'm going to say 1 minus 1 over x, 1 minus 1 over y. I will keep only positive powers of both x and y, and what this will end up giving me is a sum over delta j left, j right, n delta j left, j right, s to the delta, x to the j left, y to the j right. And great, if I can calculate this, I've got those numbers. So that's what I'm going to try to do now.
Would this work for the higher end? The simple trick doesn't have an analog for SO5 versus C.
Oh, I don't know. That's a good question. Yeah.
Probably do something.
Yeah.
Formula. Right. So while character formula, every character can be written as a something divided by something, and the denominator, if you multiply that on the other side, you would get a very compact expression for which there is an analog of positive roots, positive weights that you probably can keep.
Okay. Now this is too hard. Okay. So first of all, what can you do? Well, you can expand this on Mathematica, pick out the nth power of t, the coefficient, put it into here, and just calculate that in Mathematica, and get hold of this polynomial.
But it's an infinite.
Sure, it is. But if you go to some finite order in t, you're okay. Some finite order in t, and don't go too far up in dimension. So let's say we want everything less than delta is equal to 100. Then we can truncate that product, and then just expand out and get the coefficient of t. So you could get some states there. But let's try to do something simpler. Let's try to study the primaries.
Robert, another way you can obtain these things is to use orthogonality of characters into characters, right?
Absolutely, for sure. Yep, and done the integral.
Yeah.
Absolutely, yep.
Yeah, but when n was 2, it's really just you fix the power of x to the power jl, y to the power jl, you've got a single character.
Yep.
For n is equal to 3 onwards, you've got an infinite number of characters.
Yep.
As you say, most of them have higher and higher delta.
Yeah.
If you really want them, that's an infinite thing, right?
Absolutely, yep. Yeah. So to get the whole answer, I mean, you couldn't use this. This would give you low lying.
I mean, you could use mathematics. You could use your head.
Yes. Okay. So let's study primaries.
This positive power truncation, can you just explain once more?
Sure.
Yeah.
So let's say that we had set, we can set n equal to some value.
Yeah.
So maybe n is equal to 4.
Right.
And let's say we're interested in delta
Yeah.
less than or equal to 100.
Okay.
that means that we want S less than or equal, the power of S to some power, and that power should be less than or equal to 100 because that's counting the dimension. So when I take a look at this sum over here, I could truncate. I could go from x is equal to 0 up to 100. Everything that I'm leaving out couldn't produce something with a dimension less than or equal to 100, and then I could manipulate that. Okay, so now let's study the primaries with delta equal to 1 plus q, and j left is equal to j right is equal to q over 2. So these would be the so-called leading twist primaries. And for this case, how will things simplify? Well, the first dramatic simplification that you see is when you start to take this product over here, we don't take a and b run over all values. We in fact fix them to just be q over 2 and q over 2. So this product simplifies dramatically.
So that is n equals 1, right? In this is n equals 1.
Over here?
I mean, when you say leading twist, you're just setting, just v.
Oh, sorry.
2. Okay.
Good.
N, okay.
N plus q. And actually, n should be greater than 2 because I haven't worried about null states. Yeah. So we would have a product from q is equal to 0 to infinity, 1 over 1 minus t, s to the q plus 1, x to the q over 2, y to the q over 2. And this would give us a sum from n is equal to 0 to infinity. Let me call this Tn. And I'm going to call this chi, let's maybe say n max of n.
Sorry, how do I know that this specialization of A and B powers gives me leading twist?
So for the leading twist, what I have to have is JL is equal to JR is equal to Q over 2, and delta is equal to Q n plus Q. So I need the power of S to be accompanied with the maximal power of spin for X and Y. Shiraz?
Yeah, I was thinking Klebsch-Gordon language.
Yes?
You're picking out unique Klebsch-Gordon coefficients, right, for SU2.
Yeah, exactly.
So you could probably quickly do this analytically
Yes, exactly.
for the leading twist.
Yeah.
Because there's no normative nature, effectively. It's like U1.
Right, right.
What? Sorry, I didn't know.
See, I mean, suppose you take the dimensions, the single guy has been expanded into dimensions and spins.
Yes.
Now you're taking Klebsch-Gordons of that, but you're only keeping those things where the spins don't. If you take S1 and S2, you get only S1 plus S2. You don't keep that whole series from S1 minus S2 to S1 plus S2. You keep it in leading spin. So basically the product of 2 gives you a unique guy.
Exactly. So J1 tensor
Because
J2.
because it's just equal there.
Because it
Yes,
wants the leading.
exactly. Yeah,
So it's a very simple problem. It's basically a U1 problem.
exactly, exactly. Okay, good. So this,
Nothing. It's just like U1.
so this is now,
That was only because there is a k by 2
K by 2.
so this is now much simpler. But let's see how this formula would simplify. So if we want the leading twist, guys, in actual fact, this is the only component of momentum that we keep. All of the other guys won't produce the leading twist. So the corresponding formula, let's start to construct that over here. That would have, so this chi, some n of v, the max, the leading twist, of s, x, y. And now we will just multiply by one factor because we only have those kinds of descendants, the way that we've restricted things. The next thing that we will do is we've only kept one state from each spin multiplet. So we don't have to bother with the 1 minus 1 over x and the 1 minus 1 over y. So that thing is immediately equal to the sum of a delta, j left, j right, n delta, j left, j right, max.
Is it just going to be ways of partitioning your final spin into
Uh,
different ways?
okay, I'll show you what the counting is.
There's effectively only one quantum number and one variable.
Exactly, exactly.
It's always the highest weight state, so it's just the one-dimensional representation. So this V is being truncated to just one
Exactly.
dimension.
Right, so if you want spin S at the end, it has to be S1 plus S2 plus S3 plus S4,
Yeah.
n of those such that they add up to S.
Exactly. Okay, so what I'm going to do now is, so as you said, there's really only one quantum number now, so I'm not going to bother with x and y. I'm just going to work with s. And in this situation, let me tell you what the counting comes out as. So let me give this function a name. I will call it g, maybe n, and gn of s is equal to, and this is actually easy enough that you can plug it into Mathematica and check a pattern, and it looks like this: 1 minus s squared, 1 minus s cubed, and so on, up to 1 minus s to the n. And that's it. So meaning what? If you were to expand this thing out, the s with the coefficient n plus k, there would be some coefficient there.
That's the extra, that's the weight of the primary itself, of phi's.
Exactly, exactly,
And these are the ways of partition.
precisely.
Yeah.
So this is the number of primaries made with n phi's and k derivatives.
Sorry, I understand the denominator.
Yep.
The numerator, because
Oh, there is
phi
a
is total
The,
weight.
the, exactly,
I see.
phi gives n, and the
Okay.
denominator is all the derivatives.
Got it.
Yep.
So the denominator is the derivative.
Is the ways of partitioning.
Yes.
The ways of partitioning into S1, S2, S3, S4. If total spin has to be n, you can partition it.
Exactly. So now, good. Now, if you look at this this generating function, that looks a lot like something that you would use to count polynomials.
So your total spin is undetermined, but it has to be made up of n factors. And then you can get arbitrarily high spins.
You could put any spin onto any of the n fields, but it must add up rightly, correctly. Yeah.
That's exactly the way of partitioning an integer.
Yes.
Yeah.
Yeah. Okay. Now,
But this all works only for Euclidean, right? I mean, in Lorentzian, there's a little maybe those things don't matter for. Yeah, we're not doing any Hilbert space norms here and so on. So presumably.
no, we're not doing norms here.
So therefore,
Um,
SO31 and SO4,
Oh,
such things will.
No, but in Lorentzian you will be doing S3 times time. And so it's, even the Lorentzian Hilbert
Oh,
space
okay.
is a representation of SO4.
I see.
Right.
What were you doing?
I was referring about R31 versus R4. So in R31, the symmetry root will be SO31, so all these derivatives will be SO31 stuff. So there is not exactly SU2 plus SU2, but for this counting purposes, I think I don't care about that.
Yeah.
Lorentzian cylinder.
Operators in the Euclidean theory and states in the Lorentzian theory.
Yeah.
And the states in the Lorentzian theory are in S3.
You're right.
And so
Yeah.
it's just the same idea.
Yeah.
So I'm never talking about R31.
No, if you're talking about states, you never talk about that.
Yeah.
You'll be talking about operators.
Uh-huh. Okay. So what does this look like?
Why does it start at S square? What about 1 minus S?
Yeah, that is.
Spin 1 doesn't matter for some reason?
So basically, what it is. So I'll okay. So I'll show you just now. So if you
How about
try
null
to
states? No.
no, if you try to construct the thing. So let me give you an example of what the primary for S is 1 would be. For example, when n is 2, it would be something like this: phi d mu phi minus d mu phi phi. So it just vanishes for a real field. If you had a complex field, you would have had something. Okay, now what?
So if there's no spin 1, then is there also no spin 3?
Yeah, no odd spins. So this is like the spectrum of the Vasiliev theory.
Yeah, but then why?
But
why
then
is
1 minus S cube should also not have been there. It should be
Okay, we'll see why there's an S cubed there. I mean, it's important that there's an S cubed. Okay, now what does this look like? This looks like a counting function for polynomials, a polynomial ring, that's freely generated by something with dimension 2, 3, up to n. So it looks like a Hilbert series. So what we wanted to know was...
I'm sorry, Robert.
Yes.
I was thinking of these S's as the various representations that came with a single phi. Right? We were Klebsch-Gordening everything that came with one phi. And del mu phi certainly exists. That would have been the spin 1 for me.
Now, if you try to put that together with another phi, that'll vanish at the end.
Something I've not understood. Okay. It's not precisely my Klebsch-Gordening. I was thinking Klebsch-Gordening.
Actually, I think it is your Klebsch-Gordon. For n is equal to 2, just now, I mean, I'll do an example. So,
okay.
Yeah. Okay, so this looks like now maybe we should try to realize primaries as polynomials. That's what that suggests, that counting function. So we wanted to know, is there a realization of primaries where we can write a polynomial for each primary, and then we've got some polynomial satisfying conditions that we then try to solve. So towards that end, we use the following representation of SO42. So here's the polynomial rep. So I'm going to tell you k mu, and k mu we represent as d by dx mu, and I'm going to tell you p mu. And p mu we represent as x squared d mu minus 2x mu x dot derivative minus 2x mu. And this was already sensitive to delta. You know, there's a delta sitting in there that's actually equal to 1.
I normally do it the other way around.
I know you do. so this is like what you'd have after you act with inversion. So, okay. So now, okay. So why would I do something so odd? This is odd. Why is this a useful thing to do? Well, okay. So let me try to convince you that it's useful. The next thing is, so if we have a primary, what are we going to want? We're going to want that it's annihilated by k, but we also want to put in the null state condition. So what is the null state condition? Well, here if you calculate p mu, and this is important that delta is equal to 1, p mu comes out as x squared d squared. Okay? So if I wanted things that were primaries, I'm actually looking for things that are harmonic and translation invariant. That's what I want.
Sorry, but the null state is only for this phi, right?
For phi, exactly.
Not for this general primary.
So, exactly, but you still have to enforce that d mu acting on any phi inside that primary is 0.
Yes.
Yeah. Okay. So now let me tell you how we're going to realize this polynomial problem. So we're going to do the following. So we have n fields. So because of that, we're going to introduce n coordinates. I is going to run from 1 up to n. So, sorry, y does?
Field have mu index.
Oh, this is x mu, this is this coordinate that's sitting here. So I'm trying to give some polynomial representation. Commute these guys, you'll just get the normal conformal group. M mu nu is what you expect. Dilatation operator is x dot d, what you expect again. So that just goes over.
Yeah, you know, I'm just
Yeah.
I think what I said wrong in my way of counting is I didn't remove the descendants of the lower guys. You know, I was just counting states, but he's counting primaries.
Yep.
So also the completely symmetric descendants of all the lower guys that I should remove,
Aha.
and that will probably be good.
Aha. Okay.
Yes.
Oh, because 1 minus s is a single derivative. Is that what you mean?
Yeah, I was just taking
Yeah.
the state content of the first guy and Klebsch-Gordening it
Yeah.
in terms of states.
Yeah.
That gives me all operators, but some of them are derivatives of other operators.
Oh, good.
Okay, so
Yeah.
those have to be removed.
Yep.
Now, if I do it for n equals 2, I've got it right. Well, there's there's only one, sorry, if I do it for n equals 1, I've got it right. If I do it for n equals 2, I have to remove derivatives of n equals derivatives of something.
N equals 2.
Total derivatives, I
Yeah.
guess.
Yeah, total derivatives of lower guys. Sorry, at any n I have to remove total derivatives of lower n guys, sorry, lower spin guys at the same time.
Yeah, that's right.
And that's a self-consistent problem you could probably solve.
So what am I going to do now? Here's K mu. I'm just going to take the usual Lie algebra thing. So I've got one copy of SO42 acting on each of these coordinates. So I'm going to, so what am I going to try to do now? I'm going to study some polynomials.
I'm sorry, one last thing, Robert.
Yes.
I think what I was giving you was a formula of the number of 1 derivative plus 2 derivative plus 3 derivative up to n derivatives. Because every time you've got something that's completely symmetric, there's basically a unique way of acting derivatives that keeps it completely symmetric.
Right, right.
So I'm getting like a cumulative sum
Yes.
for my formula. I would have to take my thing and subtract it from m and n minus 1 to get you.
Aha, aha. So that's the first thing that our polynomials should satisfy. This means they're annihilated by k. What is the null state condition? The fact that each field satisfies the equation of motion. That would be the condition that d by dx mu, d by dx mu. Okay, let me put these down. For any I is 0. But finally, I need to make it symmetric. So I'm going to have one last condition, which is that x mu of I is equal to psi x mu sigma of I. So let's just make sure that we're happy with these three conditions. Here it is, the polynomials annihilated by k. That's the null state condition for each field. And this is the condition that actually we've taken the symmetric product. So we're going to now look for polynomials that satisfy those three conditions. And if you can write down a set of polynomials that satisfy those three conditions, then we can translate them back to primaries.
Is a function of n x's.
Exactly. Yep. Now, let me just put a few comments for our leading twist problem. So first of all, to get this leading twist guy with the highest possible spin, it corresponds to working with some complex variable. So we're going to use a complex variable.
Basically, you're looking at primary counting of primary operators inserted in infinity rather than LCR.
Yeah, I guess. Yep. Now zi would be maybe x.
That's why
One.
that's why it's inverted and then it's working at 0.
Okay. So by making everything a function of that complex coordinate, this is how we get the leading twist. So this coordinate, the way that I've set up my SO4, this is the one that would have m left equal to m right equal to 1/2 in the SU2 multiplet. So taking products of these will give me the right spins, the maximal spin guy. The other thing is, so by the way, as soon as we start working with just complex guys, z's and not z bars, we can already tick this off. It's already harmonic, so we trivially solved that. Next thing is, if you think about Sn, these nz's are permuted by the Sn. So they just get permuted with each other. This is what's called the natural representation of Sn. And the natural representation is reducible. And it decomposes into something that is the symmetric. So labeled by a Young diagram just with n boxes plus the hook. And the hook looks like that. Now, let me tell you what these two are. So this one, what this looks like, it's x, it's z1 plus z2 plus all the way up to zn. So that guy is obviously invariant under permuting any two z's and stays the same. For this guy, the coordinates for that, we have ZA. And what ZA is equal to, it is so let me put I'll put that to distinguish z's. Okay, so that z is z1 plus z2 plus za minus a times by za plus 1. That's what it is proportional to. And what you can see is, if you now do a simultaneous shift of everything, you get n shifts there, or a shifts there, minus a times by za plus 1. So this coordinate here is invariant under translations. That isn't, but this is.
Actually, I haven't understood this part.
Okay, so let's say, I think it's going to be useful if we take n as 3. If we take n as 3, we could take z1 plus z2 plus z3. This is an invariant under S3 on its own.
Yeah.
Then we can take z1 minus z2, and we can take z1 plus z2 minus 2 z3. If you translate z1, z2, and z3 by exactly the same amount, both of these are invariant. And that's what this operator does.
Yes, but what about this? I didn't understand how making things functions. You wanted to have the invariance under permutations.
Yes.
So anything that's a function of z1 plus z2 plus z3 is great.
Yep.
It's invariant under permutations.
Yep.
But things that are functions of these don't look like they're invariant.
Oh, good. So they're not. So what we're going to have to do is, we're eventually going to have some big polynomial in these guys, and we're going to have to figure out how to get the Sn, the Sn invariant piece out of that polynomial. That we'll do with the projection operator, and that projector will tell us how to build the primary.
I see. And what was the comment about these representations? That is.
Oh, so if you've got these n objects transforming under Sn, that decomposes into two irreducible representations. One of them is invariant. The other one is of dimension n minus 1, and it's made of these kinds of coordinates.
What is the polynomial corresponding to phi cube?
Sorry, what is that?
Polynomial corresponding to phi cube.
1. So each of these z's is going to be a derivative.
Okay.
So the translation between...
Yeah, I see. That's why I asked you why these fields are indices. So these are not phi fields.
No, they're not phi fields. These are the derivatives.
These
So
are the derivatives associated to nth phi.
exactly. Yep. So what you can do is, you could take p mu 1, p mu 2, up to p mu k, act on 1 with that operator there, and you will land up with some polynomial. And that polynomial would correspond to these momenta acting on the field phi. So
Oh, I see. That's why it's inversion, because it's a field. I mean, because it's x rather than
Multiplying rather than negative. Yeah.
yes. So now, let me just tell you one last piece of this dictionary.
So what you want to do is construct polynomials that are invariant under translation, the functions only of z. This you've already said.
Exactly. Yep.
And the non-trivial part now is to make it permutation.
Exactly. And that'll give us the formula for the primaries. Yep.
So why is P not just x mu? You have more complicated thing, right?
So
Because
the
derivatives are x mu only, right?
yeah. So if you start off with the representation where P is d by dx, the one that you're familiar with, and K would be whatever it is. Apply inversion. K will become d by dx, and P will be something more complicated. That's what we picked up for P.
P is x. So I didn't understand it.
No, P is analog of K mu, right? I mean, at the origin.
Right.
It was more complicated looking.
You mean P mu as an operator?
That.
Yeah, yeah. Yep. Now,
That's why P square has derivatives also.
So here is the translation. If you have that in terms of momentum operators acting on your field 5 naught, this will translate in the polynomial language into -1 to the k, 2 to the k, k factorial, z to the k.
The degree of the polynomial is the net.
Exactly, exactly. So that's the translation. So now let's do n is equal to 2. So let me just consider an example. Let's take n is 2.
Where is one getting these numbers from?
Those coefficients over there. What you would actually have to do is, so this formula for p, which is x squared d mu minus, so
just act them a bunch of times and just get
exactly, and you can see that when the second p acts here, now all of a sudden these derivatives can start hitting that x's, so that's why they grow so fast. Yeah.
And this can just be specialized to z's, right? Rather than
Exactly, exactly. Yep. So if we're at n is 2, what did we say we're going to do? We're going to move to the z variable, and we're going to use the hook. So the variable that we're going to build our polynomial from is just z1 minus z2. That's it. So if you want to build something now that is Sn invariant, what's the Sn invariant thing?
You can't use z1 plus z2 because it's not translational.
Exactly, that wouldn't be a primary. z1 plus z2 would be a descendant. Yeah.
Overall derivative.
Yes, exactly. So z1 minus z2 you can raise to the power 2k, and this would in fact now give you a primary, a polynomial that's a primary, and you can translate that back into the primary operator. So let me tell you in this case what is the primary operator, just because n is equal to 2, I think we are most familiar with. That's
2k because symmetry.
exactly, because it has to be symmetric. Yep. So this would be the step of projecting to the symmetric. In this case, it's completely trivial. And what you land up with is s factorial over 2 to the s, a sum from k is equal to 0 to s, minus 1 to the k over k factorial s minus k factorial squared dz s minus k phi dz k phi. And that might look familiar. So that's the form that I guess Todorov first wrote down for these currents. Yep.
If I wanted to do this translation explicitly, what exactly would I do?
Good. So expand this thing out. When you expand this thing out, you're going to get a binomial coefficient. For every single power of the polynomial, replace it by a derivative, and that's going to bring another 1 over k factorial. So this denominator comes 1 from the binomial, 1 from that translation, and that's the non-trivial bit.
So it's as simple as that. You just
Yep.
write it as sum of monomials and translate.
Exactly. Yep.
Oh, so that is this is the zk, the dictionary between zk and derivative on phi is that.
Exactly. Yep. But now what? So of course this was well known, but I don't think that there were any families written down when you have 3 fields, 4 fields, 5 fields, stuff like that. So let me explain to you how you can get those now, and it's just a symmetric group problem. So what do you have? So we said we're going to work in terms of the hook variable. So good. We're going to use those. And let's say we've got a degree k polynomial. So we've got a degree.
So if we were doing fermions, it would be basically as simple. You just keep the high spin part of the fermions.
You could focus on the high spin part of the fermions. In the last step, instead of projecting to symmetric, you project to anti-symmetric. And in fact, it all goes through. Yep.
Just to be completely sure, so this EZK there, that K is a species index.
EZK. No, that's raising it to a power.
That's
So-
raising it to,
So this would be, I could also write this as, this would just be the derivative.
So that's it. I see. And that works on all the copies. It is all of that.
Good. So
I have n copies, right?
you have n copies.
Yeah.
So here, for example, you had 2 copies. Z1 is acting on the
Each of
first.
them I see.
Exactly. Exactly. For a degree k polynomial, all that you need to do is project onto the Sn invariant. So what you would have, sorry?
In general number of variables?
Exactly. So you would have, let's say, A1 going all the way up to ZAK, so that this is a degree k thing. Each of the A's would run from 1 up to n minus 1, because it's this representation of Sn. And now you would just plug in the projector, exactly the same projector as we were writing a little while ago. A1 up to AK, B1 up to BK. So this thing would be, so let me tell you what that thing would be.
Robert, the thing I still
Yep.
haven't got in my head
Yep.
is this group theory statement. You're saying functions of n variables
Yep.
under the permutation group are either completely symmetric or they belong to that representation.
So what I'm saying is, imagine you give me n objects, x1 up to xn. Now you
Was that
permute
used,
those.
that statement? Yeah.
Yeah, that's why you have to construct this ZA like that.
So now you permute these objects. And, well, you can ask, is this a reducible or an irreducible representation?
At the moment, I'm just looking. Okay, good. Yes.
The answer is, it's reducible. If I take a sum of these objects, that's like a scalar. It doesn't mix with anything else. And if I take these other combinations, in fact, they mix with each other if you permute them, but not with this guy.
So if I take functions of n variables, they with no other conditions of these functions of n variables, under the permutation group, you're saying they transform into that plus that. Is that correct?
I'm saying that you can write them as, let's say, an x and an xa, and that thing would not transform under the permutation group, but this thing would mix with each other.
You're writing it. This is not about the functions, it's about the basis.
Exactly, exactly. Yep. And the xa's are translation invariant, precisely.
Now I understand. Now I
Yep.
understand. You're just changing language from z's to center of mass and something else.
Exactly. So these are a bunch of relative coordinates somehow.
You're saying how the relative coordinates transform under permutations.
Exactly. And the relative guys are important because they're the primaries, because they're translation invariant. Yeah.
So this basis that you took was a little, so this Z1 minus Z2,
Yep.
and then Z1 plus Z2 minus 2Z3.
Exactly.
And that's not what I would have done. I would have done Z1 minus Z center of mass, Z2 minus Z center of mass, etc.
But then you would have got n variables rather than n minus 1.
That's right.
I see.
The other thing,
Oh, I see. Yes.
so let me tell you another reason why this is a nice way to do it. You remember the representation that we wrote for Young's orthogonal representation yesterday? These guys transform in that representation. So you can happily use all of that group theory when you want to build this projector. So this projector, P B1 up to BK, A1 up to AK. Now, if we want a projector, remember we've got a sum over the group, and now we want the character of the representation that we're projecting to, but we want the trivial rep. So there's all of the characters are 1, and then we have just the matrix representing permutation sigma in this representation, so I'll just draw it like that. And this would have indices, B1, A1. And then I would take the tensor product of n copies of these. And this gives me some big matrix. I can apply that matrix to this bunch of z's and get out a polynomial. And that gives me the primary. Now, just by doing that numerically, let me show you what the answer is. So we said, what were we trying to understand? We said it.
Actually, in terms of Cockham's variables also,
Yeah.
it would be easy to write down these primaries. You would just write a symmetric functions of these guys, and then put in the last guy to be
Okay, that's a good point. That sounds right. You mean because basically if you symmetrized on these new variables, you've already symmetrized. Yeah, yeah. Oh, good point. Okay, that's a nice thing to try actually. Right.
That's one of the ASU engines.
Yes. Okay. So let me just remind you what was Gn of s. S to the n, 1 minus s squared, going up to 1 minus s to the n. When n is 2, we would just have the s squared. What's the generator? z1 minus z2 squared. So polynomials built out of that are primaries. When n is 3, we would have the s squared and the s cubed. What are they? z1 plus z2 minus 2 z3. The trouble is that's not symmetric. So we complete it into something that is symmetric. And that gives you the n cubed. And then you would take this guy and make it symmetric too. And then if you go to n is 4, now you take the next variable, do the same thing. So it becomes completely clear what are the generators of this polynomial ring. You can write down the complete set of polynomials, and then using rules like this, you can translate it back into a primary.
So this S, I mean, this is you're constructing a thing in terms of which you will construct. So you will just take S to the power of n equals 2
Exactly.
guys and then any power of these guys.
Exactly.
What is the other generator there?
The other
Just,
generator, so I'm going to write this as
right.
z12 squared.
Yes.
It's z12 squared plus z13 squared plus z23 squared.
Yes.
And then you can take any power of this multiplied by any power of that, and that gives you the full set of primaries then. And you can translate that back to derivatives, and that's a completely explicit expression. Okay, so I should say, guys, I designed this so that if we want to stop any time, I can stop. So
Yeah, we need to take you out to lunch and get back for the next talk.
Okay.
Maybe 1 o'clock.
oh, perfect. Okay, wonderful.
Does that work?
Yeah. With
So actually I'm not coming back for the talk, but I'm coming back for a 2:30 meeting.
So then maybe we should, maybe 1:45 then.
Good.
I can try to postpone but I'm not getting the other persons in the meeting.
No, let's.
You know what?
Let's do it.
I can. So I've still got like 8 minutes. That's perfect. Okay. Good. So that's for this leading twist primary. So let me tell you a few other things that you can do. You could also have done something where you take delta to be q plus 1. You take j left to be q over 2. And you take j right to be anything. So you've maximized one of the SU2 spins.
Sorry, that's one
Yep.
thing I missed here.
Yep.
You wanted to get singlets out of
Some degree k.
some degree k guy.
Yep.
And there was a unique singlet out of.
Oh, good. No, there isn't a unique singlet. So when you do this numerically, you have to break the degeneracy and you have to pick it some way. Now, one way of picking it is as I showed you over here. So now every single different polynomial that you write down does give you a different primary. One thing you could ask is, are these guys orthogonal under the 2-point function? And the answer is no, they're not. So there's probably a nicer basis you could write than the one that we've got here. This is just natural to write them all down. Yeah. Then for this set of primaries, in fact, you can again play the same games, and you can get very explicit expressions for the countings. Now you need to keep x and y in the game because there's not just one quantum number going on. You still get a ring, but in fact it's not freely generated. So there are some relations between the generators. You can write down explicitly what the generators are, and you can check that you get the right relations that you'd expect as predicted by the Hilbert series. And again, you can get explicit formulas for families of primaries with now 2 sets of derivatives acting on the fields. And then finally, what you can do is you can
Still
say,
leading retrojectory?
uh,
Yeah, this is
no,
JR.
one of the spins can be anything, just one is fixed. So it's a simplification, but not as much as leading twist. And then finally, if you try to consider the set of all primaries, so just let J left and J right be arbitrary, you still get a ring. But you need a star product on the ring, and it's basically because when you multiply two harmonic functions, the product of two harmonic functions is not harmonic. So you need a star product to make that work. So this story of the ring structure for the primaries goes through. Let me maybe make a comment on some generalizations, for example, to the vector model and the matrix model, because
So suppose we were at n equals 4, and we wanted to count all the primaries.
Yep.
Can you do that?
In practice, it's very messy, but we've got formulas for that case. In that case, what you have to do is, so we were thinking about counting multi-trace operators, and in that case, so here we were always projecting to the invariant. Here we were projecting, just count, yeah. Here we were projecting to the invariant of Sn. So what we were thinking is, imagine you ask me, you give me a certain trace structure, and these could of course be different species of fields, and you say how many primaries with this trace structure, and some delta and some spins. So it's a bit more refined than just counting everything. In this situation, you would play exactly the same game that we did, but instead of projecting to some invariant of the symmetric group, this guy is invariant under the cyclic group Zn1, and the same thing for each trace. So you would land up projecting to the invariant of this cyclic group, and that would then again give counting with that cycle structure.
Suppose I held the spin fixed,
Yes?
and I wanted to know how the number of operators at fixed spin grows with delta as a function of n. Asymptotically.
Mm-hmm.
Are those two?
So we haven't worked that out, but that is the kind of a thing that I think we'd have a fighting chance.
I think we could probably make physical predictions for this.
Ah,
Like some gas coming.
you mean fixing spin,
Yeah.
deltas, whatever you like,
Like that.
and fixing cycle structure or any cycle structure?
Just arbitrary. But okay.
Yeah.
Thank you.
By the way, I asked you this, is there a way to organize these things in terms of higher spin symmetry multiplets?
I'm sure there would be. We haven't done that.
Yeah, I suspect these things for n equals to 3 that you have written down.
Yep.
In terms of the Z1 plus Z2 minus 2Z3 product
Mhm.
and comma this other guy. I think this is probably one, and that sounds.
I guess, so for the higher spin problem, what I would try to do, I guess you don't have to do this, but I would try to use the vector model, and then I would take account of large n. And to do that, the fields that you would have, you'd have a phi I1, so some bilinear, going up to phi ik, and then the symmetry that you've got is you can swap pairs of fields, and there would be an SK that does that, or you could swap any fields inside the pair. And that total group would be the Reith product of SK for swapping the pairs, and S2 for swapping fields inside a bilocal. And when you project to that, you can match some higher spin counting just of primaries that has been done by other people.
So the question you're trying to ask is to organize end products into representations of that. So had people, is that the last part known? Do people know what?
Yeah, some of that is known. And it's related to the symmetric group of n fields, of n things. And the way you organize also naturally in terms of multiplets of the symmetric group, right?
Yes. Yeah.
It's probably going to be a finite number of representations of the
Yeah.
Right, we know when n is 2, we get just one representation.
Exactly. Yeah. Yeah.
So an interesting question is how it grows. The number of
Yeah.
n is 4, your guess was that it was 2 representations?
N is 3.
Good. Okay, so this is a natural place to stop.